Nobel Prize winner in physics Adam Rees recently confirmed that our understanding of the universe is incomplete. According to him, the James Webb telescope has made a confusing discovery that once again confirms that the cosmos does not actually behave as our models predict it should. But how can it be that the universe is expanding much faster than our standard model allows? Well, the so-called Hubble tension has been posing enormous problems for experts for quite some time. But now, scientists at the universities of Bonn and St. Andrews believe they have finally solved the mystery of the universe's expansion speed. However, their novel approach still has one crucial catch. It only works if we abandon Albert Einstein's teachings on the nature of gravity. Today, we'll show you what Webb has brought to light in the depths of space, and how this exciting alternative theory manages to solve one of the greatest mysteries in the history of research. It's been less than 3 years since Webb began its scientific mission, and yet the most powerful space telescope ever built has already managed to shake up our understanding of cosmic evolution. If you're even remotely interested in the subject, you'll have noticed that Webb has now uncovered a whole series of mysterious galaxies that appear far too large and massive for their age, just a few 100 million years after the Big Bang. Since our current models cannot explain the existence of these early galactic heavyweights, they quickly earned the infamous nickname, universe breakers. But is this nickname really appropriate? Well, who knows? Because perhaps the situation is not quite as impossible as initially feared. In fact, a new research study has come to the conclusion that the mysterious red objects are not inexplicably massive galaxies at all, but rather growing black holes. And where most of the observed light is attributable to such bizarre mass monsters, we are no longer confronted with galactic premature babies that cause our standard model of cosmology to collapse like a house of cards. And although the solution requires further follow-up observations, we currently seem to be on the right track. But unfortunately, this does not apply to another no less serious problem in current research. As briefly mentioned at the beginning, the universe is expanding much faster than our theoretical predictions allow. We owe the discovery that the universe is expanding at all to a certain Edwin Hubble, who first realized around 100 years ago that the Milky Way is by no means the only galaxy in the cosmos, and that the other galaxies are also moving away from us. In the same breath, however, this revolutionary discovery was accompanied by the no less groundbreaking conclusion that, viewed backwards, the spatially expanding universe must have had a tiny starting point in which everything was once compressed. While that starting point has since become known as the original singularity, which today forms the core of the Big Bang theory, experts in the 1990s discovered that space is not simply expanding. Contrary to all expectations, its expansion is actually accelerating. Dark energy was again postulated as the driving force behind this confusing acceleration, an equally mysterious and unexplored force that is said to counteract gravity. But how fast is the universe actually expanding? At first glance, you might think that this benign question can be answered quite quickly. But in reality, it's at the heart of a research puzzle that astronomers have been grappling with for years. Why the Hubble tension is so problematic? From a purely theoretical point of view, the matter seems clear. If we use the standard model to determine the Hubble constant, which indicates how fast the universe is currently expanding, we get a value of around 67 kilometers per second per megaparsec. The unit may sound a little strange, but bearing in mind that a megaparsec is equivalent to around 3.26 million light years, this simply means that the speed at which galaxies are moving away from each other in space increases by 67 kilometers per second every 3.26 million light years. Converted, that's 244,000 kilometers per hour per megaparsec. But unfortunately, this only applies on paper. In practice, our direct measurements in space have shown that the value of the Hubble constant is significantly higher. More precisely, studies of supernovae, gravitational lenses, variable stars, and red giants have shown that it is actually 73 kilometers per second per megaparsec. That's an impressive 264,000 kilometers per hour per megaparsec. and thus a deviation of no less than 20,000 kilometers per hour per megaparsec from the theoretically predicted value. This drastic deviation is summarized as the Hubble tension. But how can it be explained? Could it be that we made crucial measurement errors in the past that distorted the true value of the Hubble constant? Well, that's exactly what the experts wanted to find out when they used Webb to re-examine the data collected by the Hubble telescope. To do this, the team led by Nobel Prize winner Adam Rees from Johns Hopkins University in Baltimore took a closer look at variable stars, red giants, and a class of carbon-rich giant stars. Ultimately, they found that the striking discrepancy between theory and reality still remains. Accordingly, the evaluation of the most comprehensive Webb dataset to date also yielded an overall measurement result of 72.6 kilometers per second per megaparsec. The deviations from the standard model cannot, therefore, be attributed to measurement uncertainties or errors in the Hubble telescope. And Adam Rees classified his findings as follows. The discrepancy between the observed expansion rate of the universe and the predictions of the standard model suggests that our understanding of the universe may be incomplete. With two NASA flagship telescopes confirming each other's results, we must take the problem of discrepancies in the Hubble constant very seriously. Was Einstein wrong? The solution to the Hubble tension. But what could be behind this? Or, to put another way, if our understanding of the universe is incomplete, what have we overlooked so far? Well, Rees says it could be an exotic form of dark energy or dark matter, the existence of a new type of particle or field, or, most controversially, an error in our understanding of gravity. According to the research team from the universities of Bonn and St. Andrews, gravity could actually behave quite differently than generally assumed, and thus enable us to finally solve the mystery of the Hubble tension. In simple terms, the solution is based on the assumption that the Milky Way is located in a supervoid, in other words, a huge empty space in the universe. Large-scale surveys have shown that the largest connected structures in the cosmos are by no means disordered and randomly distributed, but are arranged in a network-like construct whose grid forms the so-called filaments. Together with the voids, these filaments span gigantic, virtually matter-free bubbles. A study led by Sergei Mazarino suggests that our Milky Way is also located in such a bubble. Against this backdrop, it's possible to explain the background to the Hubble tension in no time at all. To illustrate this, the researchers compare this constellation to an air bubble baked into a cake. Since the matter density around the bubble is consequently much higher, gravitational forces emanate from it, pulling the galaxies inside toward the edge of the bubble. For the expansion puzzle, this means that the galaxies are moving away from us much faster than expected because they are subject to the effects of a local underdensity. Unfortunately, however, this seemingly plausible approach is accompanied by a major limitation. Strictly speaking, such underdensities, or supervoids, should not exist at all. The standard model states that matter in space should be evenly distributed. However, the authors of the study point to a series of galaxies 600 million light-years away that are moving away from us 4 times faster than the standard model allows. But that's not all. In the same breath, the scientists emphasize that the standard model is based on a theory of the nature of gravity proposed by Einstein, and that it's conceivable that the creator of the theory of relativity was wrong on some crucial points. More specifically, this refers to the assumption that gravitational forces behave very differently from what Einstein expected. And so it came about that the researchers also used a modified theory of gravity in their computer simulation. Specifically, this is the so-called modified Newtonian dynamics, or MON for short, which was proposed in the 1980s by Israeli physicist Mordechai Milgram. MOND is actually considered an outsider theory. MOND describes the rotational behavior of galaxies through modifications in the equations of motion of matter in the gravitational field, and thus does not even require the effect of the ominous dark energy. However, the alternative theory also predicts gigantic empty bubbles in space. And that is precisely the crux of the matter. Because if gravity really behaves as Milgram expects, there would actually only be one constant for the expansion rate of the cosmos, and the observed discrepancies would simply be due to the uneven distribution of matter. However, the extent to which MOND will succeed in shaking off its outsider status in the future is, of course, another question entirely. After all, it would mean that we would have to abandon some established, basic assumptions about the nature of gravity. And before we have to say goodbye, we'd like to encourage you to click on the subscribe button. Become part of our community now to never miss a new post from us again. We'll see you soon.